Okay, lesson 25 is more interesting word problems. The first type are these age problems, and then the second type are different kinds of rate problems. So let's consider first a typical kind of age problem. So here we have one. 6 years ago, Eddie's mom was 5 times his age. In 18 years, she'll be twice his age. How old are Eddie and his mom? So the tricky part of problems like this is they are talking about ages in the past and ages in the future. And the best way to solve these problems is to pick your variables to represent the current age of each person. So we'll look at have Eddie's current age, and we'll let that be E. And then the mom's current age, and that will be M. And now the problem tells us things about 6 years ago and about 18 years in the future. So we need to think about, 6 years ago. Okay, so 6 years ago, how old would Eddie have been? Well, he would have been his current age minus 6. And 6 years ago, his mother would have been 6 years younger as well. So her age 6 years ago would have been M minus 6. Okay, and if we think about 18 years in the future, well, 18 years in the future, Eddie will be his current age plus another 18 years. And his mother also ages, and so in 18 years, she will be M plus 18. So as we go through the sentences and translate them from English into math, we need to be sure that we're using these expressions for the appropriate ages. Okay, so the first sentence tells us that 6 years ago, Eddie's mom was 5 times his age. So his mom's age 6 years ago was M minus 6. And that was equals 5 times his age. That's 5 times, and again, we're talking about 6 years ago, so his age 6 years ago was E minus 6. So that was the situation 5 years ago, and then 18 years in the future, she'll be twice his age. So in 18 years, she'll be M plus 18, and that will be twice his age, but of course he will age as well, so he will be E plus 18 years old in the future. Okay. And so now we have 2 equations with 2 unknowns, and it should be fairly straightforward to solve for the 2 ages. So let's go ahead and rewrite this one as M minus 6 is 5E minus 30, and this one as M plus 18 is 2E plus 36. And since we've just got M's here, probably elimination is one of the easiest things to do, so we'll just go ahead and subtract all of these from the top equation. So M minus M, we eliminate M. Minus 6 minus 18 is negative 24. 5 minus 2 is 3E, and then minus 66. So if we add 66 to both sides, we'll get that 3E is 42, and so that E is 14. Okay, so that gives us Eddie's current age of 14. And now we just need to substitute that into one of these equations to figure out the M. Just stick it here, so M plus 18 will be 2 times 14 plus 18. 14 plus 18 is 32, so this is 64. And if we just subtract 18 from both sides, we get 46. So Eddie is 14, and the mom is 46. Okay, so that's the kind of problems that we see with the age problems. Now the second set of problems in the chapter are called rate problems. Okay, and should be somewhat familiar to you because you know the distance formula, or this formula of distance equals rate times time. Okay, and all of these rate problems are really related to that kind of formula, but it won't always be distance. In general, what we'll have is, some kind of unit equals rate times time. And that rate, is just, think about, you're going to have units equals unit per time times time. These cancel out and you get the units, right? So it's always important to look at whatever units you're given. So it could be, a number of ounces of milk that you can drink per second, or it could be diapers you can change per minute, or whatever. But it's just some unit in some amount of time, and so it always follows this general kind of formula. Some rate times time equals some kind of job or some kind of thing, unit that you're trying to take care of. Okay, so our first example is a problem like this. Let's say that Joe can wash 4 cars in 5 hours, Tom can wash 5 cars in 4 hours, and they need to wash 20 cars. So suppose Joe works for 2 hours, and then Tom joins him. How long will Joe and Tom have to work together before they can finish all of the cars? Okay, so we've got a few things going on here. So first, we are calling these rate problems, so we need to figure out the rate at which things are happening. So Joe has a rate. Joe's rate is just some unit per time. So what kind of unit are we thinking about? We're in cars. His rate is 4 cars per 5 hours. Or we could write that as 4/5 cars per hour. Tom also has a rate. So Tom's rate is 5 cars per 4 hours, or 5/4 cars per hour. Okay, and the last thing we have is their rate together. So Joe and Tom's rate together. So in these problems, we are going to assume that Joe will continue working at the same rate of 4/5 cars per hour, and Tom will continue working at his rate of 5/4 cars per hour, and that their interaction doesn't change anything. Now, who knows? In reality, maybe, once they're working together, maybe they're really competitive and that spurs them on, and so they actually work faster, or maybe they're really chatty and they spend a lot of time talking, so it slows them down. But we're not talking about reality, we're just talking about theoretical models here. So, theoretically, they work at the same rate, and so when they work together, we're just going to add their rates. So if this were like Joe's rate of J and this were Tom's rate of T, then when they work together, they're just going to have a rate of J plus T, or 4/5 plus 5/4 cars per hour. Okay. So when we solve the problem, those are the rates that we're going to use. So let me pull out a new piece of paper. Okay. And so we know that they need to finish 20 cars, and this is what happens. Joe starts working, and he works for 2 hours. Okay, so if Joe is working for 2 hours, here's the start time. And for 2 hours of time, Joe is working alone. Okay, so the amount of cars that Joe will finish in that time is, well, Joe is working at the rate of 4/5 cars per hour. And he's working for 2 hours. So hours cancel with hours. And he finishes 8/5 cars. Okay, after those 2 hours, Tom joins him. And for, H hours, Joe and Tom work together. Okay, so how many cars will they finish when they work together? Well, their rate together was the 4/5 plus 5/4 cars per hour. And they are working for H hours. And so that's how many cars they will finish. And if you add the cars that Joe did by himself with the cars that they did together, we know that they need to finish 20 cars. They're not going to stop working. This H ends when they've finished 20 cars. So we add those together, we get 20 cars. So we have cars plus cars equals cars. That's a good thing. If the units don't match, you know that you've done something wrong. Okay, so now all we need to do is just solve for H. So we have 8/5 here. I'm just going to drop the units because we know they match here. Okay, and then we're going to need to change this one to 20ths. So multiply this one by 4/4 and we'll get 16 20ths. Multiply this one by 5/5 and we get 25 20ths. Okay, and so let's subtract. Well, let's multiply everything through by 20. That'll make everything easier. Let's add these first. So we have 8/5 plus 41 20ths H is 20. Multiply everything by 20, and that way we can get rid of our fractions. So, okay, so 5 goes in 24 times, so this is 32 plus 41H is 400, or 41H equals 368, and divide both sides by 41 and we get H equals 368 divided by 41, 8.975. Okay, so Tom, and this is, okay, if you forget what the units are, just go back and look here. This was H hours. This has to be hours. So Tom and Joe, or Joe and Tom, work for almost 9 hours together. I mean, we could convert that to hours and minutes. It's so close to 9 hours, a few minutes that are short of that are irrelevant. Okay. So that's that problem. Okay. Our next problem. After breaking his crown, Jack realized that he could now only fetch pails of water at a rate of 3 pails in 40 minutes. Working with Jill, Jack found that together they could fetch water at a rate of 4 pails in 20 minutes. So what was Jill's rate of fetching pails of water? Okay, so we have Jack's rate, and he can fetch pails at the rate of 3 pails per 40 minutes. And Jill has a rate, but we don't know what it is, so we'll just call it J. And together they have a rate of 4 pails in 20 minutes. Now remember from our previous problem that we're going to assume that Jack continues to work at the same rate and Jill continues to work at the same rate when they work together. Okay, and so to figure out Jill's rate, we know that when they work together, if we put Jack's rate of 3/40 pails per minute, and we add Jill's rate in pails per minute, we are going to get a rate of 4/20 pails per minute. So we've got pails per minute and pails per minute and pails per minute. All of the units match, so we've got an equation. All we have to do is solve for J. Okay, so to do that, we just need to subtract 3/40 from both sides. So J is going to be 4/20 minus 3/40. Multiply this by 2/2. So we'll get 8/40 minus 3/40, which is 5/40, or 1/8. So Jill's rate is 1 pail in 8 minutes. Okay. Okay, and next we're going to see a lot of problems like this. This is straight from example 25.4. I didn't make it up from a fairy tale. So 5 workers can do a job in 8 days. So how many workers would it take to do 3 jobs in 7 days? Okay, so we have the worker rate. So the worker rate is kind of difficult to see. So we have sort of like a single worker, and we have like 5 workers. Okay, so we don't exactly know how fast a single worker can do it necessarily. We know that 5 workers can do 1 job in 8 days. And if you think about it, this is just like the previous problem. Now, if we had single workers working at a particular rate, let's say that rate was S jobs per day, then we're just putting 5 of them together down here. So 5 of those single workers would be equal to 1 job in 8 days. So the single worker's rate, with just one person by himself, would be 1 job in 5 times 8 days. That would be the rate for a single worker. And that might be how you want to think about solving these problems. And now they're going to ask us, well, how many workers is it going to take to do 3 jobs in 7 days? So we know that for a single worker, 1 worker can do 1 job in 40 days. So we might say 1 job is to 40 days for a single worker. And now we want to figure out how to do 3 jobs in 7 days. Okay. Well, this is where it gets tricky. And so rather than trying to convert everything to single days and looking at proportions, how you may have thought about solving it in the past, we kind of want to refocus our thinking and change this a little bit so that we can use our units to take advantage of the situation. So if you look in your book, you would see that they kind of solve it in an interesting way, and I'm just trying to help you see how they're thinking about it. Okay, so they don't really put anything about the single worker. It's kind of implied in there. But what they do is they say, okay, so the number of jobs that is accomplished is going to be the rate at which a single worker can do a job times the number of workers, and that would be like the rate for 5 workers, times the amount of time that it takes to get those jobs done. So then if we think about the rate, let's just solve this for rate, then the rate would be jobs divided by workers times time. That would be the rate. Okay. So when we think about the rate, we're not just going to think about it in jobs per day like we normally think about rates. Instead, we're going to think about the rate in jobs per worker time. So in this particular instance, we'll want to think about it as jobs per worker days. So that's, the number of workers times the number of days, how many worker days equivalents you have to do the job. Okay, and so because we have lost the unit of workers over here, when we are just thinking about jobs per day, and this 5 kind of gets lost and the units gets lost in there, and it's hard for us to see, and so solving the problem without that unit of workers in there becomes problematic because you can't see the units. But when we solve it this way, where we can see the units, it's a lot easier to solve. Okay, so if our rate is jobs per worker time, then we're going to rewrite this rate as being 1 job and 5 workers times 8 days, or 1 job per 40 worker days. And now when they ask us how many workers will it take to do 3 jobs in 7 days, we can just think of, okay, well, I'm going to have to multiply this thing by workers and multiply this thing by days, both of those, workers and days, to cancel out the units that I have in the denominator. So I have my rate of 1 job per 40 worker days. Okay, so we will say how many workers. We don't know that, but we do know that we're going to have to multiply by W workers to get workers to cancel out with workers. And we want 7 days, so we multiply that by 7 days, so that days cancels out with days. And the number of units that we have left is jobs, and we want it to be 3 jobs. So how many workers will work for 7 days at this rate to get 3 jobs done? And now we just have to solve for W, the number of workers. Alright, so we can just multiply both sides by 47. So the 40 cancels with the 40, and the 7 with the 7, and we'll just be left with W. And we have 120 sevenths. Alright, and let's figure out what that is. 120 divided by 7. Okay, so the number of workers that we need is about 17.14 blah blah blah. I guess we can't really have a fraction of a worker, so in this case I would probably answer 18 workers. they had 252 gallons of milk. This would feed 42 infants for 12 days. Then 14 more infants were placed in the nursery, and 48 more gallons of milk were provided. So how long is this milk going to last them now? Okay, so this is similar to the last problem. So we need to think about this milk, and it's being drunk at a certain rate. Okay, we have days, and we have gallons, and we have a number of infants. Okay, so our rate is going to be measured in gallons per infant day. Okay, so in this particular instance, our rate is going to be 252 gallons in 42 times 12 infant days. And let me calculate what that is. 42 times 12. So that's 252 gallons for 504 infant days. Okay. So, now they tell us that 14 more infants are placed in the nursery, and 48 more gallons of milk are provided. And how long is this milk going to last? Okay, so we take our rate of 252 gallons for 504 infant days. We've got 14 more infants that are placed in the nursery. So there used to be 42. Now there's 14 more infants. Now there's 56. So that's 56 infants. And they're asking us how long will the milk last. We don't know, but it's going to be D days. And the number of gallons that we get, they tell us, is 48 more gallons than we used to have. So it's 48 more than the original 252, or 300 gallons of milk total. Okay, so this was the 252 plus the new 48 that they got, and this one was the original 42 infants plus the 14 that were added. Okay, so we've got gallons on this side, gallons on this side. Everything seems to match, and so now all we have to do is solve for D, the number of days. Okay. So we've got 252 times 56 divided by 504. I have is 28 times D is 300 gallons. So if we divide both sides by 28, 300 divided by 28 is approximately 10.71, and D was measured in days. Okay, so hopefully that is a good example of the different kinds of rate problems that you'll encounter, and so good luck with those.